So, ladies and gentlemen, a very interesting highlight coming up next here on the innovation stage. We want to look into a very technical topic, and I'm super excited to hear their solution because our next speaker represents a startup bringing fresh innovation into advanced manufacturing. The Vibrocut GmbH, or GmbH, how we call it in Germany, presents ultrasonic and oscillation-based assisted process that open up new possibilities for material processing and efficiency. Please welcome here on stage Oliver Georgi, Managing Director of Vibrocut. Please ask your question via Slido if you want. Oliver, stage is yours.
Hello, thank you. Today we will talk about hybrid machining and cutting technology. So we go to the cutting edge and the challenges and things that happen there. So the Vibrocut company develops and sells systems for hybrid machining. But what is hybrid machining? So we have two areas in the company. We have one area which is called oscillation technology. And this means we add an oscillation to an existing cutting process, like turning or drilling or milling. And this oscillation has a frequency of about 100 hertz and a stroke of several millimeters. And we have another technology which is also called hybrid machining. It's ultrasonic technology. And here we add ultrasound to an existing process to improve the efficiency. And ultrasound means a frequency of about 20,000 hertz and a few amplitudes in stroke. But I will tell you or explain you in certain slides about our systems, the tool systems we use for hybrid machining, and also some applications that you can see the advantage in cutting technology. So the products in these areas are one product for Vibrocut Oscillate, which we use in turning lathes for oscillation-assisted turning. And then on the right side, you see Vibrocut Ultrasonic, which is an ultrasonic device or tool system, which we use for machining centers, for drilling, milling, and grinding. And we have also a special device for deep hole drilling. So let's start with the ultrasonic assistance with the Vibrocut Oscillate for the tooling system at first. So you see on the left or the right side, you see a tool holder. And inside this tool holder, there is a so-called transducer integrated. And the transducer produces ultrasound inside the tool holder and generates the ultrasound through the tool, and this is applied to the process. And this tool holder has an inductive energy transmission, so it's contactless, and that the tool holder can rotate. And it's also possible to change this tool holder in the machining center automatically. And besides the special tool holder, we have a certain cabinet where our ultrasonic generator is inside for control loops of the ultrasonic system, that it works reliable. And our unique selling proposition here is that we have systems with a high power, so we can produce high power ultrasound to assist the process. And in addition, we have a sensor inside the tool holder which measures process data and which measures also the properties of the ultrasound. And behind, we have a control loop of frequency and amplitude to keep the ultrasound properties reliable at all times. And the system is like a tool system setup, so it's possible to retrofit existing machines, but it's also possible to equip new machines with the technology. And here we have an animation of the system at all. So next to the machine, you see here a small cabinet. In the small cabinet, there is the ultrasonic equipment inside, the generator, and also some security stuff. And when you look inside the machine, especially in front of the spindle, then you have in front of the spindle a so-called stator for the energy and signal transmission. And you have the tool holder, which produces the ultrasound. And the system has also an interface to the machine tool so that you can use it within the NC code to switch it on to set parameters by the NC code in the automatic production. And let's talk a little bit about applications of the ultrasound. So the first applications are in the region of drilling and deep hole drilling of metal materials. So here we have one slide for an application example. Here the material is a casted aluminum, and the tool is a diamond tool, and the diameter 8 millimeters. And here we analyzed how is the impact of the ultrasound to the drilling process. And the ultrasound is capable to reduce the process forces significantly. You see it on the right side. So there you have the gray line, which is the force produced by a conventional process. Usually it increases with a higher feed. And then you see a yellow line, which is the ultrasound with an amplitude of 15 microns. And then you see an orange line, which is the ultrasound with 25 microns. And you clearly see that the feed force go down significantly when you use the ultrasound, and it is reduced by more than 50% in this application. So when you have a lower process force by drilling a hole, then you can increase the feed rate or the productivity quite easy, and you can have feed rates more than 50% increase in the application, and that's why you can have a lower cycle time and save money to a higher productivity. And also in some cases it's quite important to get out the chips of the hole, and also the ultrasonic keeps a removal of the chips out of the hole, and then you can have also a higher process reliability. We also have a video here. So on the top, there is the ultrasonic assisted process. On the lower, there's the conventional process. And you see quite simple that the ultrasound increased the productivity, especially the feed rate. And here in this case, of course, when you have a certain amount of holes, then you are certainly quicker when you use ultrasound. And then you can save time and save also money in the production. And a second topic is also burrs on exit of holes. So it's a topic in series production. When you have burrs like on the left side of the picture, then you need deburring processes. And the deburring processes cost money and time. And when you use ultrasound and you decrease the forces, then you have a lower burr building on the exit of the hole, and you can avoid deburring processes and also save money in the series production. And the last application for ultrasound is deep hole drilling of a nickel-based alloy. Here it is a Monel K500. It's used mostly in the chemical industry. And when you drill difficult to cut materials like nickel-based alloy, every time tool wear is a certain issue. And you see here also pictures on the right side. So the top row is the conventional process, and the tool is even gone after one hole. We do it to 3 holes, and you see that there is a big amount of tool wear on the flank of the tool. And when you use the ultrasound, the tool wear is decreased dramatically. And here in this application, you have 3 times longer tool life when you use the ultrasound for this difficult to cut material. And this on one side saves money for the cutting process, but on the other side you also have a higher process reliability by drilling such materials. So to sum up the potential of ultrasound in drilling of metals, you have lower forces, which leads to higher cutting values, higher productivity. Especially in case of deep hole drilling, you have a higher process reliability. When you have difficult to cut materials, then you have a higher tool life. And it's also possible when you go for deep hole drilling to have an improved straightness. And one topic on top is the reduction of burr formation on exit of holes. So let's skip to another application. This is grinding of brittle materials. So we can use the same equipment in a machining center, but we use grinding tools, diamond tools, to grind certain materials like silicon glass or like aluminum oxide. So these are materials, they are difficult to cut on one side, but on the other side they are quite sensitive regarding cracks in the material and so on. So this is a challenge for grinding process at all. And here we have also an effect of ultrasound. So usually the tool moves over the part, and we use ultrasound, we have an additional movement in axial direction, and therefore we have an additional removal of the material. And also here we can reduce the process forces significantly. And afterwards, here we can have a higher process reliability, smaller cracks in the material, and a better removal process at all. So also a certain application. This is an application of a wafer chuck in the semiconductor industry. And there is a task to have a deep hole drill, a deep hole in the material of a diameter 4 and 180 millimeters. And in conventional machining, it was not possible to produce such a hole. And therefore, we use the ultrasound here in this application. And then we have a 100% reliable process to produce such hole in this difficult material. And in addition, we can increase the feed by 60%. So we have also a more productive process by using the ultrasound. And one additional slide is about grinding the face of such a part. So here, we use also a shaft tool to do the grinding. And on the right side, we have again analysis of the force of this process. So again, you have the red line with the conventional force. And then you have different amplitudes in yellow and orange line. And also here, through the ultrasound, we significantly reduce the process force. And here in this application, it's quite useful because then you have a higher process reliability. And especially in these materials, the process reliability is quite important because every time the parts are quite expensive, and it's very important to have a good quality here in this case. So also to sum up this area of applications, so when you use ultrasound and grinding, then we have higher productivity, higher process reliability. It goes also in a positive way for the tool life, and we have a self-sharpening effect of the tools also. And of course, we can decrease the cracks in the parts and have a higher part quality at all. So the last application for the ultrasound is ultrasonic stir friction welding. Stir friction welding is a quite new process to connect two materials in case of aluminum materials. And there, the tool goes inside the materials and do friction and producing heat. And then the material is plastified and connected together. And when you use ultrasound in this case, then it is possible to reduce the forces, to have no specific machines for the stir friction welding. Then you can use it also in conventional machining centers. So you use the same tool holder, you use a shaft tool for stir friction welding, you implement the equipment in a conventional machining center, and then you can do a welding process in the machining center. And on the right side, you see just an example process. So it's a blind seam in one part, and you see the tool. Now the tool goes inside the material, do the plastification, and afterwards, it has a feed direction to produce the seam and the connection between two parts. And the benefit is that you can have a quite easy integration in machining centers. And on the other side, you have a quite high quality of the seam regarding the strength of the seam and regarding also the connection of the materials. So we can skip. So that's the topic of ultrasonic assisted machining. And the next example is for oscillation-assisted turning. So here we have another product. We have a tool holder, which is mounted on the turret of the machine tool. And the tool holder, you see it here in this slide. You mount it on the turret of the machine tool. And the tool holder does an oscillation movement in feed direction of the turning process. And we use this one to have smaller chips in the machine to have a higher process reliability. And the tool holder is mounted on the live tool place, and it's just a mechanical device. So it transforms the rotation of the turret of the live tool place into the oscillation movement. And that's why we can have quite high amplitude and quite high frequency. And this tool holder is easy to implement also in existing turning lathes. So it's a live place tool holder. You can put it in the turret, and then you can easily start the process. So also good to retrofit existing machines. But let's look to have on the effect of such a system. So when you have long chips in a machining and a turning lathe, then you have problems with process reliability. So one point, there can be machine downtimes because the user has to stop the machine and manually to remove the chips. On the other hand, you can have problems with automation because the long chips tangle around the tool, tangle around the workpiece. Yeah, so on the left side here, you have a bad chip breaking behavior of the conventional process. It's here a steel process. And on the right side, we have different applications or different configurations of our oscillation-assisted process. So on the left side, we can have an interrupted cut, which means the stroke of the oscillation is bigger than the feed. And that's why with each oscillation, we produce one single chip. And you see it on the top left picture that you have reliable single chips with the same size. And when you then increase the frequency to the lower picture, then of course you have smaller chips because you have more oscillation movements. And one point then we do in the cutting technology, we have the right side. So there we have a smaller feed than the smaller stroke than the feed, and the cutting edge remains into the material, and we have some kind of breakage points in the chip where the chip tends to be break. And you see it on the right side also, you see these elements, but sometimes there are 2 or 3 of these elements connected together. But all in all, you also break the chips in the machine. And also when you increase the frequency here, then you have satisfying more short chips. But all pictures on the right side solve the chip breaking problem in the machine, but you can even adjust the chip size of the machine with our technology. And why is this important? So especially in serious production, when you do not solve the chip breaking problems by the cutting edge, by changing the feed, then such a system produces a quite reliable chip breaking behavior. Also, you have different material batches. Also, you have a difficult to cut material, and also you have tool wear. So you can secure the chip breaking behavior with such a technology because you force the chip to break with the oscillation movement. And also here we can have some videos. So this is a machining task of aluminum, longitudinal turning, and on the top you have the oscillation movement switched on. And on the bottom, you have the conventional machining process. And it's the same cutting data, the same cutting edge, but just on the top, the oscillation is switched on, and it completely solves the chip breaking problem here. And one special topic is the machining of lead-free brass, because there are some regulations of lead-free materials. And when you machine brass, and there is lead-free material, then you get issues with the chip breaking. And to make it easy, you have on the right side a chip produced by the conventional machining, which tends to tangle around the tool. And on the right side, you have the chip produced by the oscillation technology. And here you clearly see that we solved the chip breaking problem. And then there's the possibility to have a high process reliability, to have an automated process with the unmanned production. So it's quite easy to implement, and it's a clear problem solver for the chip breaking problem. And also here we have one example. I have a video later on for plastics. So in plastics, it's impossible to have a good chip breaking behavior when you use a different cutting edge, when you use different feeds. And when you use our device, even in plastics, you can have short chips. So we see it also here in the video. The left side, the conventional process, right side with the oscillation movement switched on. And you see just one chip for the conventional process, and you see short chips with a switched on oscillation movement. So here it's quite impressive, also why the tangled chip goes around the part and is a big problem in machining of plastics or turning of plastics. So here a clear solution, quite easy to implement into the turning lathe. And again, to sum up the advantages, so we can increase the machine availability by lower downtime, especially in serious production. We have a higher process reliability because the parts do not tangle around the tools, around the part. They do not scratch surfaces or something like this. In many cases, we enable the automation and the unmanned production because we solve the chip breaking problem. And there's also a certain issue about health of the operator of the machine, because when the operator tends to manually remove the chips, then he can cut the fingers, and it's also an issue of the health of the operator. So thank you for the audience, was the last slide, and I'm happy to answer some questions about these new technologies.
Thank you very much. Oliver, first of all, amazing. So especially with the chips, that was understandable, even for me as a non-technician. We have a few questions. So which materials come into account, for instance, wood applications? Is that something that would be feasible as well?
Yeah, for the ultrasound or for the other topic?
For the ultrasound assisted.
For the ultrasound. So we have a current project where we will investigate the wood machining. So for now, there is no knowledge about how the ultrasound affects the machining of wood, but there will be knowledge end of this year. Yeah.
Very good, very good. So is the electric power requirement for ultrasonic drilling higher than for the conventional process?
In total, it's lower, because the ultrasound reduces the productivity, and when you have a machine tool, the higher power consumption comes from the machine tool itself. Yeah, and the ultrasound has just 200 or 300 watts. Yeah, and when you have a higher productivity and you produce a part in a lower cycle time, then you save more energy in total.
Awesome, awesome. What do we have here as well? Is there additional wear and tear on the spindle because of the oscillating assisted turning?
Yeah. So this is a quite common question, because usually our vibrations are not good for the machine tool at all. But for both technologies, we have some kind of decoupling mechanism inside the device, so that nothing of the vibration goes back into the spindle of the machine.
Very good. One question for me that I prepared at least. How difficult is it to implement your solution? Because I mean, I have an existing machine, or do I have to buy a new machine?
Yeah. Usually we have both ways. We have the equipment of new machines. There we collaborate with machine tool suppliers. When we go to the retrofit side, then we do the retrofit on ourselves or together with the customer. So the oscillation unit just takes some minutes, because you put it in and the machine has already all capabilities. And for the ultrasound, we need nearly 1 day to implement, because there's electrical function, we need to set up some cables and so on. But all in all, 8 hours or 1 shift is the implementation time.
And what we haven't tackled so far is the economic side of the whole thing. So how much is such a solution, and what are the savings? I mean, we have seen the technical improvements, no doubt about it, but you mentioned a few business opportunity as well. So what is the cost related to the output?
Yeah, so for both technologies, the return of the invest is quite well. So for both technologies, we have a return on invest from less than 1 year, which means when you solve an automation problem, then you can even not count the money. But when you solve machine downtime, then you can calculate how often is the downtime per shift. And usually we have a return on invest from less than 1 year for both technologies.
Awesome. That's it for my question. No more question from the audience, at least we are empty here. Thank you so much. Oliver, it was a pleasure having you. Interesting topic. Good luck for the rest of the fair, good conversations and good growth for your company.
Thank you very much.
Bye-bye. Big applause, ladies and gentlemen.